Hello guys, welcome back to another video. Today we are going to discuss the topic of sulfonamides and sulphones. So without further ado, let's get started. So sulfonamides. Sulfonamides are employed as a generic name for the derivative of para-amino-benzene sulfonamide. So how do we draw a sulfonamide or a sulfonylamide is? First we draw a benzene, then a para-amino. So in this position there is something, and in the para position we have an amino group, that is an H2 group, para-amino benzene sulfonamide. So sulfonamide would be S double bond O and H2. How do you remember this is sulfonamide? Amide is C double bond O and H2, but since it's a sulfone we will give it a S double bond O double bond O. So we will get a sulfonamide, or also known as sulfonylamide. Now for the mode of action. So in the basic thing we will know is there is a derivative called PABA, that is para-amino benzoic acid. With this we will add another substituent known as teichoic acid. So when we add teichoic acid and PABA in the presence of folate synthase, first we will get a dihydroteichoic acid followed by some other reactions which will give us a dihydrofolic acid, and then dihydrofolic acid is converted into tetrahydrofolic acid in the presence of dihydrofolate reductase. Now this was folate synthase and this is dihydrofolate reductase. So in this we will have the inhibition of folate synthase by sulfonamides. Now for the in detail mode of action, now bacteria synthesize their own folic acid. As compared to humans who take folic acid from their diet, bacteria have to synthesize their own folic acid. For this they will take the PABA, which is para-amino benzoic acid, as a constituent from the medium. Now sulfonamides are analogues of PABA. It means that they are very similar to PABA. So what they will do is they will inhibit bacterial folate synthase. Therefore folic acid is not formed and number of essential metabolic reactions will suffer. Now what are these metabolic reactions which will suffer? It is the production of purines and then nucleic acids which will suffer. Now sulfonamides competitively inhibits the union of PABA with pteridine residue to form dihydroteichoic acid. So as we said earlier, PABA will unite with pteridine residue or teichoic acid to form dihydroteichoic acid. Now this dihydroteichoic acid will conjugate with glutamic acid to produce dihydrofolic acid. Now also sulfonamide may itself get incorporated to form an altered folate which is metabolically injurious. So these are all the modes of actions of sulfonamides. Next, moving on to the SAR of sulfonamides. Now what do you mean by SAR is? It's the structural activity relationship. So it means like what the structure says or how the structure rules the activity of the group. So now as we know, this is the structure of sulfonamide. We have the para-amino, and in the first position para-amino benzene sulfonamide, that is sulfonyl group and amide group. Now here we will have a R group attached right here. So the sulfonylamide skeleton is the minimum structural requirement for the antibacterial activity. Now the sulfonylamide skeleton is this part right here. So this is the minimum structural requirement for antibacterial activity. Now the amino group and the sulfonyl group on the benzene rings are essential and should be in the first and the fourth position only. So the amino and the sulfonyl group should be in the first and fourth position only. Next is the N4 amino group. So in the fourth position, this N. So the N4 amino group could be modified to be a prodrug, which are converted to free amino acids, free amino functions in vivo. So this NH2 group can be converted, keeping this N as it is. If this group is changed, it can be modified to a prodrug. So it can be converted into the active form once it goes in vivo, that is in the body. Now next is the sulfur atom. This atom right here should be directly linked to the benzene ring. Now there should not be any carbon in between it. It should be directly attached to the benzene ring. So it should be directly linked to the benzene ring. Next we have the replacement of the benzene ring by any other ring system, or the introduction of additional substituents on it will decrease or abolish the activity. So this ring right here has to be a benzene ring. If you substitute this ring with some other ring, or if you add extra substituents to it, it will decrease or abolish, that is to reduce or stop the activity of sulfonamides. Next we have exchange of SO2 group and NH group. SO2 NH group by CONH reduces the activity. So if you substitute this group right here, SO2 NH, with CONH, this will reduce the activity. Next we have on N1 substituted sulfonamides, activity varies with the nature of substituent of the amino group. Now if here the NH and this R group is substituted, now based on the nature of the substituent at the amino group, the activity will vary. With substituents imparting electron-rich character to SO2 group, bacteriostatic activity increases. Now if this R will give a electron-rich character to this SO2 group, then the activity will be increased. Next we have heterocyclic substituents lead to highly potent derivatives. So if you add a heterocyclic substituent right here in this R group, it will give a highly potent derivative. While sulfonamides which contain single benzene ring at N1 position are considered more toxic than heterocyclic ring analogues. Now if this R group you will give a benzene ring, these are considered more toxic as compared to the heterocyclic rings. Next we have the free aromatic amino group. So the free aromatic amino group should reside in the para to the sulfonamide group. That is, this free amino group should reside in the para position or the fourth position. Its replacement at the ortho or meta position results in the compounds devoid of antibacterial activity. This means that instead of giving the para position an NH2 group, if it was given in the meta or the ortho position, this compound would be devoid of any antibacterial activity. That is, it will have no antibacterial activity at all. Now, the active form of sulfonamide is the ionized form. Now, maximum activity that is observed is between the pKa values of 6.6 to 7.6. So the active form of the sulfonamide is always ionized, and the maximum activity is observed between the pKa values of 6.6 to 7.4. Now substitutions in the benzene ring of the sulfonamides produces inactive compounds. So as we said earlier, if the amino group is given here or any other substituent is given here, this produces an inactive compound. Now substitution of free sulfonic acid, that is SO3H group, for sulfoamido function destroys the activity, but replacement by a sulfonylic acid group and acetylation of the N4 position retains back the activity. Now just in case, this is our sulfonylamide group. Now instead of SO2NH we add SO3H. This will reduce the activity or destroy the activity. But instead of this, if we give SO2H, this will increase the activity. Along with this, we can also do acetylation of the N4 position. So here we will give NH and then C double bond O, or some acetyl group right here. We will get the same activity which is retained back. Now swiftly moving on to the classification. Now we have classifications based on two things. One is based on the basis of site of action, and one is on the basis of the onset of action. Now on the basis of site of action, we have sulfonilamide for general infections. Now for general infections, we have sulfonilamide, sulfapyridine, sulfadiazine, sulfamethoxazole. So we will remember sulfadiazine and sulfamethoxazole along with sulfapyridine. Sulfonilamides for urinary tract infection, we have sulfa-isoxazole and then we have sulfathiazole. So how we can remember this is UTI. So U will keep it separately, T and I. So sulfathiazole and sulfa-isoxazole. Next we have sulfonilamines for intestinal infections. So for intestinal infection, we have phthalyl sulfathiazole, succinyl sulfathiazole and sulfasalazine. So we'll remember we have ST for intestinal. So intestinal ST. So we have sulfathiazole, that is in two different things we have succinyl sulfathiazole and phthalyl sulfathiazole, and then we have an extra sulfasalazine. Next is sulfonamides for local infections. For local infections, we have silver sulfadiazine, then we have sulfacetamide and mefenamide. For dermatitis, we have dapsone and solapsone. For sulfonamides in combination, we have this one combination, that is trimethoprim and sulfamethoxazole. We will call it cotrimoxazole. Next is on the basis of duration of action. So on the basis of duration of action, we have the long acting sulfonamides, that is approximately for 7 days. We have sulfadoxine, sulfamethopyridazine. For intermediate acting, we have 8 to 12 hours, that is sulfamethoxazole. Short acting, we have sulfamethiazole and sulfoisoxazole. For special purpose, we have sulfacetamide, sodium, mefenide, silver sulfadiazine and sulfasalazine. Now let us start with the structure of sulfadiazine. So as we can see, sulfa and diazine. So first we will draw the basic structure of a sulfonamide, that is a benzene ring. Along with this, we have an NH2 group in the para position. In the other side, we have S double bond O, N connected with an H, and connected to this we will have the R group. So R group right here is diazine. Di means 2, azine means nitrogen. So 2 nitrogens. So we'll give 1 nitrogen this way, 1 nitrogen this way, and we complete this 6-membered ring. So this will give us a sulfadiazine. Now the uses of sulfadiazine are toxoplasmosis, meningococcal infections and rheumatic fever prophylaxis. Next we have sulfamethoxazole. So as we can see, we'll break the word into sulfa, meth and oxazole. So we will write first the basic ring structure, that is a NH2 group right here, then a SO2 group, and then NH. Attached to this we will have a methoxazole. Now for oxazole, we will draw a 5-membered ring, oxygen here, ox and azole, nitrogen right here, and in the other position we will give a meth, that is CH3. So this is a structure of sulfamethoxazole. Now the uses include bacterial infections and drug allergen. So next up we have sulfadoxine. So for sulfadoxine, first we will draw the basic ring structure. Then S double bond O and NH. Attached to this we will have a 6-membered ring. We will draw a pyridine ring. Then we will give 2 methoxy groups. Here one, right here one more. Next we have the sulfapyridine. So sulfapyridine, we will draw sulfa and a pyridine group. So we will have the basic ring structure. S double bond O, and H, and then a benzene ring. With this we have a N right here. So this is our sulfapyridine. The use of sulfapyridine, they were used previously for dermal infections. It's also used for dermatitis, herpetiformis, and pyoderma gangrenosum. Next we have sulfacetamide. So as the name suggests, sulfa and acetamide. So first we'll draw the basic sulfonamide ring. S double bond O, and then H, and then acetamide. So C double bond O, CH3, acetamide. So this is a sulfacetamide. It is used for acne vulgaris, seborrheic dermatitis, and conjunctivitis. Next we have phthalyl sulfathiazole. So first we will start with the basic ring structure. That is, we have a NH2 group here, but we'll keep this empty for a reason. Then we'll have a S double bond O, and H group. Attached to this we will have a thiazole ring. Thia means S, azole means N group. So we will have a 5-membered ring. In this we will have a nitrogen and a sulfur. So this is a sulfathiazole. Now for phthalyl we will add to this NH, we will add a C double bond O, then a benzene ring, and down we will add another C double bond O, H group. So this is a phthalyl sulfathiazole. So this is a phthalyl group, this is a thiazole group, and then we have, this is a sulfonamide. So phthalyl sulfathiazole. Now the uses include dysentery, colitis, and gastroenteritis. Next we have sulf-isoxazole. So as we know, oxazole is oxygen and nitrogen which are very close to each other. So sulf-isoxazole is, this position will be changed. So we have a benzene ring, NH2 group, S double bond O group, double bond O, and H. Then we have a isoxazole ring, that is 3, 4, 5 group. Then here we have an oxygen, here we have a nitrogen, and then a CH3, CH3. So this is a structure of sulfo-isoxazole. It is used as a UTI anti-infective agent. Next we have sulphones. In sulphones, the first one we have is dapsone. So in the structure of dapsone, since it's a sulfone, so it means it has a benzene ring, a NH2 ring, S double bond O, another benzene. Along with this we have a NH2 group. So this is the structure of dapsone. Now the MOA is, it inhibits folic acid synthesis by inhibiting dihydroteroate synthase and incorporation of PABA into dihydroteroate. Now the uses includes leprosy, nocardiosis, anti-malarial, anti-infective, and anti-inflammatory agent. Next up we have the structure of trimethoprim. So for the structure of trimethoprim, first we will break the word trimethoprim. So this trimetho means methoxy, and then prim means it is a pyrimidine ring with diamino group. So first we'll start with the pyrimidine group. So pyrimidine is a benzene ring with alternating nitrogens and diamino, that is 2 amine groups. So benzene ring. Then we'll attach this to a CH2 and then another benzene ring and then 3 methoxy groups. 3 and one more right here, OCH3. So this is a structure of trimethoprim. MOA of trimethoprim is, it inhibits dihydrofolate reductase, that is DHFR, and it prevents the conversion of dihydrofolic acid to tetrahydrofolic acid. Next we have the uses. In uses, it is used as an anti-leprotic, that is leprostatic. Next we have the synthesis of sulfur isoxazole. So in this corner we will draw the structure of sulfur isoxazole. So we have the basic structure, benzene and an NH2. This way we have S double bond O, then NH. Attached to this we have an isoxazole ring. So oxazole ring here, then CH3 and a CH3 group here. This is a structure of isoxazole. So first we will start with this part right here, and we will add a chlorine here. So we will get, and here we will get a CONH. So we'll start with this structure right here. So we will take 4-acetyl-amido-benzene, 1 sulfonyl chloride. This is sulfonyl chloride. In the fourth position we have acid-amido, that is this part, acid-amido-benzene, sulfonyl chloride. To this we will add 3,4-dimethyl isoxazole 5-amine. So we will add this structure basically right here. So we will add 3,4-dimethyl isoxazole 5-amine. So when we add, and there would be removal of HCl. So there is a Cl removed from here and an H removed from here. We will get this structure right here. Now next step is removal of this CH3. So we will do hydrolysis. So there would be removal of COCH3 along with the OH, and an H would be given here. So we will get sulfur isoxazole. Next we have the synthesis of dapsone. So the structure of dapsone is one benzene ring, a S double bond O, a benzene ring, an NH2, another NH2. So for this we will take this part. Okay, so we will add a 1-chloro-4-nitrobenzene. So instead of amino we'll take nitro, and this side we'll add a chloro group. So 2 of these and sodium sulfide. So what will happen is chlorine is removed from here and chlorine is removed from here, and it will attach to these 2 sodiums. So there will be removal of 2 molecules of NaCl, and there will be condensation. So we will get this group right here, that is bis 4-nitrophenyl sulfane. To this we need to add double bond O. So we will add chromic acid, which is an oxidizing agent. So it will add NO2, SO2, benzene, NO2. Now we have to reduce it. So NO2 will be reduced to NH2, and we will get dapsone. Next we have the synthesis of trimethoprim. In the synthesis of trimethoprim, first we will draw the structure of trimethoprim. So it is benzene, a CH2, another benzene. To this benzene we have a nitrogen right here, NH2 here, and an NH2 here, and to this one we have OCH3, OCH3 and OCH3. So we will start with this ring here. So we will take 3,4,5 trimethoxybenzaldehyde. So as we see here, this CH2, instead of this CH2 we are taking a benzaldehyde. So we'll add zinc in the presence of hydrochloride, and this will undergo reduction. So we will get CH2 and OH. So CH2 and OH. Now we will let it undergo chlorination in the presence of thionyl chloride, that is SOCl2. So this OH will be replaced with chlorine. Next we will take ethyl cyanoacetate, that is CN, CH2COO, C2H5, and there would be removal of carbon dioxide and hydrolysis. So what will happen is this will be removed and this part right here will be added. So we will get ethyl cyanoacetate added here, chlorine removed, and the NC, that is the cyano group, removed. So we will get this. Then there would be addition of HCOO, C2H5 in the presence of NaOH. So what will happen is this C which is attached to one H right here, one H right here, and a COOC2H5. So this H will be replaced by CHOH. So C connected to COOC2H5 and a double bond CHOH from this part right here. So then we will get, in bicyclization in the presence of guanide group, we will get removal of ethanol, so we will get this structure. Then in the presence of POCl3, there will be chlorination here, OH will be converted to chlorine, we will get this structure, and then there will be ammonium added and removal of HCl. This one is removed and an NH2 group will be added, and we finally get a trimethoprim. So that's all we had for today. I hope you enjoyed the class. We will be back with such videos very soon. Until then, goodbye. Have a nice day.